A PID controller, which stands for Proportional Integral Derivative Controller, is a type of feedback control system used in various industries to regulate and control processes. It is a fundamental and widely used control algorithm in automation and control engineering. The PID controller calculates an error signal as the difference between a desired set point and the current process variable, PV, which is the value being controlled. The controller then adjusts the control input to the process, typically in the form of a valve position, motor speed, or some other actuator, in order to minimize this error and bring the process variable closer to the desired set point. Here's how the components of a PID controller work. Proportional, P, term. The proportional term generates a control output proportional to the current error. It provides a corrective action that is directly proportional to the error magnitude. A larger error leads to a larger proportional response. This helps reduce the steady-state error but can lead to oscillations around the set point if used alone. Integral, I, term. The integral term accounts for the cumulative sum of past errors and produces a control output to eliminate any steady-state error. It is useful for handling system biases or long-term disturbances that the proportional term alone might not be able to address. The integral action integrates the error over time and gradually corrects for any accumulated offset. Derivative, D, term. The derivative term predicts the future error based on its rate of change. It acts to dampen the system's response to sudden changes in the error. This helps in reducing oscillations and improving stability. The derivative action anticipates the future trend of the error and provides a control output to counteract it. The combined action of these three terms allows the PID controller to balance responsiveness, stability, and steady-state accuracy. The controller gains, proportional, integral, and derivative constants, need to be tuned to suit the specific system being controlled. The process of tuning involves adjusting these constants to achieve the desired balance between fast response and stability. There are various methods for tuning PID controllers, such as trial and error, Ziegler-Nichols method, Cohen-Kuhn method, and more advanced techniques involving computer simulations or optimization algorithms.